Welcome back, geometry students, to part 2 of section 5.3. We're talking about points of concurrency of bisectors. Now, this section we're going to be talking about concurrency of angle bisectors, and this is the theorem related to that. So if you haven't seen part 1, make sure you guys check that out, talking about the circumcenter. Now we're going to be talking about angle bisectors instead of perpendicular bisectors. So what is an angle bisector? Well, it's something that splits an angle into two equal angles. So we're going to go ahead and try to draw a couple of those. Now, again, the best way to do this would be if you had a protractor. You would measure the distance and then divide that by 2 and then draw an angle. Okay, so I'm not really sure what's going to happen here as I do this without a protractor, but I'm going to do my best. Okay, so I'm going to go ahead and draw this. Now, you can extend these lines through. It doesn't matter, but I think it's going to look something a little like this. And you can tell I didn't do this great because this angle is a little bit smaller than this one, and it's supposed to be bisecting it, meaning equal. So I clearly did something wrong. I'm guessing it was this. So I'm going to go ahead and try this one more time just to make it a little bit more accurate. Okay, something like this. And I think it's going to be a little bit better. I can't really see my own writing. There we go. My hand was covering up. That looks a little bit better. So you can see that each one of these angles is being bisected. That means they're equal. So this is going to be equal. This is going to be equal. This one's a little iffy, but bear with me. Just pretend. Okay. So we have 3 lines meeting up, and it doesn't matter if you extend these lines or not. Okay. For this one, but they all meet in the same spot, or they should. Now, this spot is special for a couple reasons. Now, if you look here and we draw a circle, okay, the circumcenter, the perpendicular bisectors, we drew a circle. Now we're going to draw another circle, but what's going to be different in this case? Well, what we're going to do here is instead of drawing it around, circumscribed around, we're going to draw this inside. So it's going to be an incenter is what it's called. What is going to be special about this particular circle? Well, and you can tell mine's a little ugly. I didn't do a fantastic job with the angle bisectors. But what should happen is this circle should be on the inside, the center of that circle. So, boy, I really kind of missed the boat here. You can tell that I should have raised this one up. So I'm going to go back and just show you that it does matter. Accuracy matters, so I know you're like, well, how am I supposed to know as I'm doing this where exactly it should be? Well, I mean, I think most of the problems, last year I got a ton of questions like, what are the problems going to look like? I just want to know what the problems on the test are going to look like. A lot of it has to do with just identifying. You should be able to identify the types of lines that are drawn. So if you see lines that are drawn like this, you know that they're angle bisectors. If you see a circle on the inside, then, well, I haven't got done explaining this, but you're going to know that it's a certain property. So this is an inscribed circle. Okay, and now I did a much better job with the circle as the reference. This is a special POC called the incenter. Okay, because it is on the center of an inscribed circle. Okay, now, remember how we drew the radiuses before? So we used this like light purple or light pink color, okay, and we drew these little radiuses, okay, so we're going to try to connect the radius here and connect the radius here, okay. Now, if you connect a radius, it makes a 90-degree angle. Don't get this confused with the perpendicular bisector. It's not a bisector at all, but these are the radius. I really wish I used a different color at this time. And radiuses, as we know, are all equal. So, what do we know about the point of center, the point of concurrency of an incenter? Well, let's go ahead and break this down right here. Well, we know that, we already talked about that. Each one of these things that we just drew is the radius of a circle. Okay, so this radius of the circle is 90 degrees, and they're all equal to each other because it's a radius, and radiuses are equal within the same circle. But what does this distance represent? In this one, it represented, in perpendicular bisectors, it represented that it was equidistant from the vertices of a triangle, okay, the point of the circumcenter. Well, The incenter is equidistant from what? Is equidistant from the sides of a triangle. Okay, so the other one was, circumcenter was the vertices. Okay, so up here, this was the vertices. This one is the sides of a triangle that is equidistant from. Okay, and these are just kind of cool properties. You can draw a circle on the inside of any triangle, and that triangle is going to be known as the incenter, which is equidistant from all three sides of the triangle. Kind of a cool property, especially if you, I don't know, you're designing certain mechanical parts and you need it equidistant for electrical purposes. That would be a good property to know and to have handy. So that is the incenter of a triangle. So example 3 is kind of a combination of all of these just to be able to identify some of these things. Now we're looking here at this and we see several things going on. One is we see that we have some angle being bisected. So we have 3 angles being bisected and they all meet in the same place. Okay, that's a big clue. Okay, we also see that we have these perpendicular lines all meeting up at that same spot. Okay, so what's going on here? Well, it's asking us, it's telling us GE is 2x minus 7. So this little line is 2x minus 7. It's telling us that GF is x plus 4, and it wants us to find this missing angle there and find, or not angle, but that missing distance there, and also the value of x. Well, what's going on here? I've been saying that a couple times, but haven't answered the question. What we have going on is an incenter. Why? Because it's the meeting up place of 3 angle bisectors. Why else? We could draw a circle on the inside, have it touch only in 3 spots, okay, to the triangle, and its green dot, its center, its center is going to be where the 3 angle bisectors meet up. Now, what does that make these 3 lines that we highlighted? Okay, which I probably should have chosen a different color, but this pink will do. What does that make those? That makes those all radii. Radiuses, however you want to say it. It makes them all the same. So these distances are all the same. What does that mean? Well, that means we can set these 2 distances equal to each other. Those 2 radiuses, because they're equal, we can set them equal to each other. 2x minus 7 is equal to x plus 4. And then we can solve for x. So we're going to subtract x from both sides. We get x minus 7 equals 4. Then we add 7, we get x equals 11. We have our first answer. And now what we do is if we're trying to find the length of GD, you'd think, there's nothing to input, but there is. Okay, it's the same distance as GE or GF. GF's a little bit easier to solve, so I'm going to substitute the value in for x, and I get 11 plus 4 equals 15. So all these distances are going to be 15 equals 15. Okay, so quick recap. Incenter, you can draw a circle on the inside. It's where the 3 angle bisectors meet up, and that incenter is equidistant from the sides of a triangle. Quick recap for part 1, if you guys watched that. Go watch that if you haven't watched that yet. It's perpendicular bisectors. They split the side in 2 and are 90 degrees. Where they meet up is the center of a circumscribed circle, which means it's drawn around the circle. And that point of concurrency, called the circumcenter, is equidistant from the vertices of a triangle. So these are equidistant from the vertices. Hope you enjoyed this video and makes it a little bit more clear. We're going to do some more examples coming up soon with some CUDA worksheet tutorials. So make sure you watch that. And be good, be kind, be true, be nice, and be honest. Have a great one.